Now, let me walk you through our guiding pillars for teaching and learning coding. Our pedagogy is based on two well-known learning theories, constructivism and constructionism. Constructivism conceives of learning as a process in which learners create knowledge in their minds as they interact with things and people, I guess, in the world around them. Constructionism, the second theory, extends on the first one to include the idea that a good way to support the building of knowledge in one's head is not only to interact, but actually to build something in the real world, whether that's a computer program, a robot, a drawing, a story, or a musical composition. So constructionism was developed by researchers at the MIT Media Lab in the US, which is also the birthplace of the very popular block-based coding language Scratch, which some of you may be familiar with. So we're following a similar approach to Scratch and have made creating and building with code really core to the experience of learning with imagi. And guided by these two theories, we use various principles in our teaching model. One of these is discovery learning, which allows students to learn by tinkering with code, modifying others' projects, and receiving instant feedback. In the imagi platform, you can create private classrooms for your students where everyone can publish their projects, and students can tap on these projects, discover the code behind them, modify them, and learn from their peers or from you, the teacher, as part of this process. The Imagi mobile app also has a community, a global one actually, where children from around the world can share their coding projects featuring their interests and passions, and they can inspire each other and learn from each other this way. Now, one of the criticisms of constructivism actually comes from the lack of data to support that the teaching technique of pure discovery works. So we also think that guided discovery is more effective, especially for beginners. This is why we provide teaching materials that you can use with your students. They start with the basic building block of turning on just one pixel, and then step-by-step guide the teacher and the learner on an exploratory journey through which you can discover more and more advanced and interesting concepts. Helpful error messages are also provided in the code editor, and this is also an example of guidance. So we try to help you figure out how to improve your code and get it to work. Of course, besides the guidance, there's also space for personal exploration, like I mentioned earlier, and learning with imagi is not limited to the exercises we provide. Another important principle is that of building knowledge. So I encourage you and your students to try multiple times, to test your code multiple times and understand how a specific code snippet works by tinkering with it. So for example, when we introduced the for loop used to create a rainbow here on the left, we prompt students to make changes to the code that they're given and see the results. They can play, for example, with the range, bounds, or they can even change how the call variable is used. So instead of having it here in the second slot as in the first code, put it in the first slot, which is actually the row index, and see what that results in. And you can see the result of that here on the right side, where actually the purple line, instead of being a horizontal line, it changed into a vertical line. And so this way, by tinkering with the code and getting this quick feedback and quick actually visual feedback, you can build the knowledge in your head. We have built the system this way on purpose so that you can make changes and experiment and get quick feedback. And it's okay if you or your students don't understand every detail. This actually doesn't matter. What matters is that the more projects you create, the more chances you will have to understand and the better you will get. Learning to memorize definitions and theories or other formal representations of knowledge often strips away the meaning. So just go ahead, tinker with the code, don't be scared to break it, and that way you and your students will learn the most. Another example of building knowledge is actually the matrix M, which is the first things that we will learn about. So this will make more sense in a minute. But M is a list of lists, but we don't formally introduce this concept until much later in the coding journey, when you have probably encountered and used M a lot, and used lists in different occasions. And so you have probably started creating this knowledge about lists in your mind already as you've interacted with them. So another important idea is to keep the learning relevant. When students have intrinsic motives for learning, when they engage not for external rewards like grades and status, but because they really find the activity interesting and gratifying, then they become more likely to attach meaning to their work, explore new topics, and persist in the face of learning challenges. So we make the learning relevant as we believe this provides intrinsic motivation. This is why we embed cultural trends into the learning. For example, projects like the ones you see here linked to games like Among Us or Minecraft characters, favorite movies and apps, are examples of how we keep projects relevant to students' interests. When COVID-19 started, we've also seen a number of public service announcement type projects like a mask emoji or a project about washing your hands that students were creating. Something else that we always try to emphasize is that there are multiple correct representations of knowledge, or different ways to reach the same outcome. So if I go back to this rainbow example, we can actually look at 3 different ways of making a rainbow. First, by setting the color of each individual pixel, which I don't show here, but you can imagine what you would look like. Or if you can't, we will see it just in a few minutes. Then the second way here in the middle is using a single for loop. And the third is introducing the concept of nested for loop and a color list. If the second and the third approach don't make sense, don't worry, we will actually talk about these in a bit. So there's no one right answer when creating and when coding. The idea of the learning process is to have the opportunity to explore and learn about different possible answers. In this case, different ways that code could be written to achieve the desired result, and eventually the advantages of one approach over the other. But focusing on optimization is not the goal in the beginning. As a final learning principle, which isn't derived from constructionism or constructivism, but is one that we believe is super important, is to learn together with a community of like-minded people in your classrooms, among your students' friend groups, and through online communities.